coffee break, unfortunately, but I think we should keep the chat and the Zoom link going, and I'm not sure. I'll let Johannes take it from here.
Hello.
Hello.
Yeah, I mean, we have 2 hours. Maybe somebody wants to get a coffee or a beer. Just tell me something. I have, if I understand, power now to mute people or to do something. I have no idea. Do I have?
Yeah, that's right. So let's see. As I learn, it's not easy to moderate. So we will help you, for example, browsing through the chat if there are questions. You can also set your view in a gallery mode, so you see most of the people. It's still the panel. You will see there are 3 panels, so you don't see them all. So if somebody raises a hand, you'll have to go back and forth between these 3 panels. And I think us will help Johannes, at least by pointing, okay, there is a hand raised by this person or this person. So Anton, I'm not sure, Nigel is. And indeed, Johannes, you should keep you can keep the answers to a certain length, but you can also let the discussion go on if people are interested. And
Okay, so I have to admit I never did this. I mean, a discussion on Zoom is actually usually a nightmare idea. So, but Emil, if I understood correctly, you wanted me to sort of start with 30 minutes introduction so that we have ideas, what would be questions and so on. Okay, so I'm trying to share now my screen. And I hope I find it.
You found it? Yeah.
Yeah, so it's visible. I just prepare the chat. Okay. Okay, so maybe I should say that it's a bit of an abrupt change from the last talk to now, because these methods which go under KK-theoretic bulk-defect correspondence principle, these methods, they are really geared for one particle systems, for one particle approximation. So really we are on very different ground, and I think at some point there should be a very nice discussion about what is the overlap between the two. But I understand maybe not today, but later, I don't know. We have 5 discussions.
But tomorrow I'll talk about interacting. I'll moderate the discussion about interacting systems. So I guess we can discuss it then.
Okay. So why does this not move here? I hope you can see. So let me just to give you some ideas, let me just more or less give you an overview of what I think I would consider to be the bulk-defect correspondence principle. Right? It's relating topological invariance to 2 physical systems. That's the basics. And the bulk boundary correspondence is maybe the most prominent example. Right? It relates topological quantities of a solid or of an insulator, which are attached to its interior, to topological quantities which you would localize and which you would attach to its boundary. But I think there are more examples, and this was probably also the reason why Emil proposed to call it bulk-defect correspondence, because it doesn't have to be bulk boundary, it can be bulk corner. I mean, there are these higher order topological insulators, and I will say a little bit more about this. But it can also be totally different systems. For instance, Levinson's theorem, where you have an appearance of this correspondence principle in scattering theory, comparing the free motion in potential scattering to the bound state system. And then there are, I think, directions which connect other invariants than what we usually call the strong invariants. For instance, when you look at quasi-crystals and you look at the gap labeling, then there is a correspondence principle which relates this to phazon motion in these quasi-crystals. Everything actually built on the same kind of mathematical theory, which I will just summarize a little bit. And I hope that during the discussion, somebody will come up with more systems of this type. And I mean, there should be more, and there is actually more. Now, I know that there are physicists which are really interested in the physical aspect behind it. And so there is sort of a correspondence between mathematical language and physical language. And if you just boil it down, then you would say topological invariance, I mean, translates into robustness. And the typical conclusion will be that there is a non-trivial topological invariant in one system, let's say the bulk system, and that would imply that there you have some robust resonances on the boundary. That's maybe the essence. Okay. So as I told you, everything is about one particle approximation. So we are looking at the Schrödinger equation and a non-relativistic Schrödinger equation, or a wave equation if we want to describe wave media. In principle, this should go in exactly the same way. And what's important is that, well, the main player therefore is the Hamiltonian, not a vacuum state, but the Hamiltonian. And the Hamiltonian is a linear operator. And so linear operators living in operator algebras, it's very natural to say, okay, our topological features of solids, they should be just given by the algebraic topology of the operator algebra, a theory which has been developed and sort of can be summarized in non-computative topology. And Nigel has told us a lot about it this morning, and that's quite useful now. Now, I would like to point out that this actually means that we will, at least today, focus on a topology which corresponds to C-star topology. Later in the week, if I understand correctly, there will be issues about Sobolev spaces and so on. So we go into different fields. But let's say the first step, the first essence concentrates about a C-star topology. And one of my questions will be, why should we take a C-star topology? Well, let me just summarize mathematical ideas, the basic mathematical ideas. What do we need for a correspondence principle? Well, we need two C-star algebras describing two physical systems. And we think of them to be designed in such a way that operators in these C-star algebras, they are related to physical properties of the systems. So in most cases, which I know, actually, one of these C-star algebra would be the observable algebra, and so would contain, or having affiliated to it, the Hamiltonian, or some sort of variant. Okay, so I will talk about this a bit later. And so an example would be one of these algebras which Nigel also told us a little bit. So his notation was a bit different. It would be a cross product of an algebra of potential functions. So I have the potentials which describe my solid, my insulator. This cross product in the tight binding approximation would mean that I have translations which are perhaps twisted by a magnetic field. And then I will have place for internal degrees of freedom like spin. It's not very important I would say right now, what really the precise definition of this algebra is. But what is important is that we have a physical idea about it, that this is really the algebra which should describe the physics of my insulator, for instance. And the second important ingredient is exactly what Nigel also was talking about, is an extension. Namely, these two physical systems, they are linked by an extension, which means they are linked in a sort of indirect way. They are linked because there is a third algebra, E, which sort of was an algebra morphism from E onto the algebra A, such that the kernel of this morphism corresponds to a copy of J. So this is not totally natural from the point of view of physics, and it has to be looked for, I would say. I mean, when do I have two physical systems which sort of are linked, or talk to each other via such an extension? If I have one, then I can do my game. And what is this game? Well, this game is that, well, if I have algebras, I can look at their topological invariants, which are given by elements, which are given by their K groups. So I have a K group for A, I have a K group for G, for J, and then I have this fantastic homomorphism, which links the two K groups, that of A to that of J. And Nigel has been mentioning, these are these homomorphisms which had errors which went downstairs or upstairs in his diagram with the 6 K groups. And that's the essence of the correspondence principle. The idea is that the physical topological properties, they will be encoded in elements of the K groups, and these will be then related by this boundary map. Now, there are many different formulations of K-theory, and I will not tell you all. And we were also hearing about one by Trout, for instance, which can also be useful in this context. And there is a picture by Bessemer and Loring. But I pick out 2 of them, which I like very much in this context, because they let appear the classes almost naturally as physical objects. The first one is the K-theory of Fundala for insulators. So if you have your Hamiltonian describing an insulator, then that means that you make the assumption that it has a gap, and we move the gap to 0. So the Hamiltonian has a gap at 0 energy. And then it's exactly an element whose homotopy class defines an element of the Fundala K0 group. So it's a self-adjoint operator, which is invertible, and the Fundala K-theory is just a functorial way to turn the group of homotopy classes of self-adjoint invertibles into a group. And so the first invariant, which we'll look at, will be just the Fundala class of the Hamiltonian. And then on the boundary, I like very much a different picture, which was advocated by Christopher Max and his co-authors, namely in terms of Kasparov K-theory. I will not explain exactly what is Kasparov K-theory, but it's a bivariant functor, so there are 2 algebras in it. And if the first one is the complex numbers of the real numbers, then it's one formulation of K-theory. And for that, we need to write J Hilbert C-star modules, which is nothing else than a Hilbert space where you replace the scalars by a C-star algebra J. And the scalar product will be J valued. And then I have a Fredholm operator, which has this property that square minus 1 is J compact. So the notion of compact operators generalizes from Hilbert spaces to Hilbert C-star models. And I want this difference to be J compact. So these two elements, they define classes in KK1C of J. And this class would be 0, and that's important, if this square of this Fredholm operator is 1 on the nose. And then there is this way of describing the boundary or the defect K-theory class. Well, the original Hamiltonian had a gap. So associated to the gap, there is a spectral projection. And now I take the spectral projection of the operator H hat, which is the Hamiltonian lifted into the extension. This operator will not necessarily be, this spectral projection will not necessarily be 0, because the lifted operator will not necessarily have a gap. And so the part of the C-star algebra of J which is projected out by this projection, together with the lift of the Hamiltonian, defines the KK class, which is the defect invariant. Now, we can just at this little formula now see immediately the key interpretation of the bulk boundary correspondence, namely that if our boundary map sends the Hamiltonian or the Fundala class of the Hamiltonian to 0, then the extension, the lift of the Hamiltonian must have spectrum at 0. And this spectrum is the spectrum of resonances, which are, if you wish, localized to the algebra J and robust against perturbations.
Ralph,
So, yeah.
I was wondering, do you want the boundary to be 0 or non-zero to have spectrum at 0? I thought the non-trivial invariant forces some spectrum to be there in the bulk.
I didn't understand this question. Can you?
You wrote if the boundary is 0, then the gaps must be filled in H hat.
Oh, no, you're completely right. Oh, sorry.
If delta is non-zero, then the gaps must be filled.
Yes. I'm sorry.
That's a typo, right?
That's a typo. Yeah. So here, if this element does not vanish, then H must have spectrum. Yeah. So if this element does not vanish, meaning that it's actually topologically non-trivial. I'm sorry. There are other versions of other pictures of this boundary map. I like the one with KK theory because it looked nice, because it just gives me on the nose what I expect, namely an operator which has spectrum or not at 0.
Johannes,
yeah,
can I interrupt? If you go back one slide,
yeah,
I think you already point here really general principles where you say that the defect, in fact, defines a Kasparov cycle. And perhaps that's true with any defect one can deal with. It doesn't have to be boundary corner. At the end, it's of this type. It's a cycle, like you write here in a...
Yeah. So are you saying that, I mean, what I wrote works for any extension, right? I don't need the interpretation.
And
I mean,
here you can, perhaps you even can calculate what this cycle is and tell us what it is, no? For, let's say, the simple lattice system. The rotational algebra.
If the system is simple enough, I can calculate it, yes. But of course, in general, take any extension, then it's going to be hard.
But in this case, just with the, let's say, 2-dimension with the boundary, this should be the Dirac operator, the 1-dimensional Dirac operator. post-cycle.
No. There, I think you think on the dual picture.
Okay.
Or well, yeah. So what I would have in mind, if you, for instance, take the standard bulk boundary, so that it would really be the lift of the standard Hamiltonian, meaning the compression of the Hamiltonian to the half space.
Yes, but then this Kasparov group can be calculated. It has a finite number of generators, and now we should have can be expressed this one in terms of those generators, those finite generators.
Oh, and then you identify the generators or the generator with the Dirac.
With a defect, exactly, with a defect.
Mm.
So the defect is in fact a cycle in the KK theory.
Sorry, could you maybe say exactly what you have in mind for A and J? And
yes. So we have this HKK element. It defines a element in the one of the Kasparov groups, and these Kasparov groups have finite generators. So this defect invariant can be expressed in terms of those generators, and you can tell this defect is this or that or that.
Yeah, you still need the way I presented it, this module, right? I started nevertheless with a Hamiltonian in the bulk. So the Kasparov class, which I wrote down, depends on the Hamiltonian in the bulk. Now, are you saying me that?
Oh no, yeah.
Forget about this one.
Yeah, so this defect is set by the sort of asymptotic bulk. So bulk is like the asymptotic part of the H hat. And whenever you hold that asymptotic part fixed, then the boundary defect, it's always this this Kasparov cycle.
I see, okay. So to take always the same bulk Hamiltonian as done. Shall I go on?
Yes, please.
Yes. Okay, so now I was telling you that there are other pictures of this boundary maps. So the first one I wrote down is a very famous one, which you can see in Emil and Hermann's book, where you use the standard K-theory, or it's the complex version. And there is another one, since I was forced to moderate something KK. Namely, you can view everything in KK. So you can also identify the Fundala K-theory with KK groups. And then you have a very nice, but extremely abstract version of this boundary map. Namely, it's simply given by the Kasparov product multiplied from the right of the extension class. I should say that whenever I have extension, that defines a KK element, and KK element with A in the first slot and G in the second slot. And then there is this very abstract and powerful method to write down the boundary map. The other question, of course, is, can I calculate that? And sometimes you can, but okay, so, and then I should say, of course, there are similar formula, closed formula for the Fundala and for the Boltzmann-Loring picture, which have a little bit the advantage of being very uniform in each symmetry class. They look sort of the same way.
Let's see, I
could make a comment here about this, namely, all these different formulas could be understood because there's exactly one boundary map in some sense. If you want to have a natural map from the K0 of A to K1 of J, no matter which picture of K0 and K1 you are using here, you can prove that there is, well, all these natural transformations are just integer multiple of the boundary map. And this means if you have any formula which is natural for extensions in a formal sense, So if you have a map between these extensions, then there should be a commuting diagram. If your formula is natural, and if it gives the correct boundary map for one example, let's say for complex numbers as A and function the circle for J, so for the cone extension, then it will be a correct formula for the boundary map. Because any natural transformation is a multiple of the boundary map.
Yes.
So this might be a way to understand why all these different formulas must exist. It doesn't really matter which picture you're using.
Yeah.
You have no choice in what you're doing here.
Yeah, one very quick comment, because one thing that we want to figure out, is there anything beyond these C-star extensions when we talk about bulk boundary? So this comment already, goes in that direction.
Can you keep this question for later, Emil?
Yes.
Because I think that's a good question. I just wanted to say that my personal point of view is also that, of course, I have these different pictures and they're all equivalent. But since I want to have contact to physics, the different ways they look, I think, play different, give different inspiration, let's put it this way. Okay, so I don't know whether I should go through this example because it's sort of the old example of the bulk boundary correspondence, but I thought I should present at least one example. Yeah, so as I already told you, if we look at the bulk algebra and think of it as the observable algebra of a solid in a magnetic field in the tight binding approximation, so meaning that we look at the configuration space which is discrete, namely ZD, then there is a natural candidate for the algebra, which is sort of fixed apart from one input, namely, what are the potentials which we would like to allow? So this little C here is the algebra which encodes the potentials which are okay. And there could be discussions whether they should be all kind of local potentials, or whether they should be periodic, or whether they should be quasi-periodic. So these discussions would fix this little C here. And then we want to describe something on the boundary, and we model the boundary as being the boundary of half space. So before, the space was non-compact in all directions, extended in all directions, and now we restrict the space to half space. So we have only Zn-1 cross the positive numbers, which is of course a sub-semigroup of this group ZD. And so the extension is naturally the sub-semigroup cross product instead of the group cross product. And it sort of can be understood that this lifting now a Hamiltonian into the extension can be understood as restricting it to half space. So it's a very natural model. Then it turns out that the ideal, J, is the same type of algebra, one dimension lower, namely along this boundary. So the boundary is only Zn-1 cross a point. That should be Zd-1. And that's, so this is the extension here for the boundary correspondence, which was the standard boundary correspondence. So everything is very natural. And to have another example, I wanted to discuss the bulk corner correspondence. So it's sort of bulk in quotation marks for some reasons which will become clear now. Namely, the bulk systems, they are Hamiltonians living in three-dimensional space, and the corner system will be something which lives in one-dimensional space. So you have to think of the corner as something which is cornered between two transversal plane boundaries. So I start with three-dimensional space. I cut through two transversal plane boundaries, and they corner me give me a quarter part. I think that's easy to see. And then the important information here is that you need that these standard bulk boundary correspondence is trivial. You need that if I look at the restrictions of the Hamiltonian to the half spaces, that these restrictions, or the lifts, if you wish, that they have a gap in the spectrum near zero, which then means automatically that the bulk invariant, the standard bulk invariant I was looking before, namely the Fundala class of the Hamiltonian, is no longer related to the corner invariant. So that is a question which is a bit open, okay? And the topological invariant, which replaces the bulk invariant, is the pair of two Hamiltonians restricted to the two different half spaces. And this is very natural because we just said that the bulk Hamiltonian does not have topological information because we require its restrictions to half planes to have gaps in the spectrum. So everything can only be derived from this pair of restricted operators. And so we just follow now the same procedure as before, except of saying that the algebra is given by the pairs of operators which are the lift of one operator in the bulk. The extension is obtained by just restricting the three space to a quarter space, or to one-dimensional space across a two-dimensional quarter space. And then the ideal will be just one-dimensional space. So I think this is a very nice example of the bulk boundary correspondence, although there is a little twist. The twist being that we don't really have something bulky. We have something which is related to these two compressions on the half spaces.
But H can still be non-trivial, right? Can you hear me?
Yeah, I hear you, yeah. H can, yeah, that's right. H can still, I shouldn't say H is trivial. I would say that what is trivial is the boundary map of the class of H applied to the half space systems.
One thing I find interesting and confusing here is that I mean, this is a codimension 2 problem, so I expected to get like a shift by 2 in K theory, but instead you just get a shift by 1, like before. Yeah. And that's just, I mean, maybe that's just a nonsense remark.
No, it's not a nonsense remark. The reason is actually, I mean, I have one exact sequence. Mm-hmm. Okay, I don't have two exact sequences. It's not like a little spectral sequence or something. Mm-hmm. So a big business about topological insulators is symmetry protection. Okay, and I think I cut this whole slide now short by saying that it can be implemented and very well in all kinds of situations, and just the same kind of idea that goes through by putting just symmetry restrictions on the elements we are looking, provided that the extension we have is in its whole invariant. So if I have symmetries, they should apply to all three algebras, and they should commute with these maps IQ. So everything up to here was, I think, quite nice. And now comes something which I think needs more discussion. Namely, we have a very abstract bulk boundary principle, which relates topological invariants living in very abstract group a priori. And now we want to know what these invariants mean. And this is also related to what Nigel was talking about, namely that we want to also have other measures to measure these invariants. And here, I mean, if we in physics do a measurement, then we get a number. And so it's not surprising that also here, what we're actually looking for is to get topological invariants, which are numerical. So we look at, it means to obtain topological invariants out of, numerical invariants out of K-theory classes. That is one question. And there are many answers to that question, and Nigel also has discussed this. But we need a little bit more, I think, or we want a little bit more. Namely, we want it in such a way that if we get a number measuring the topological invariance of K of A, that this number should, I mean, this way of getting the number out of the K groups should be coherent in a way that it defines a sort of a dual theory, a theory dual to K theory. So I mean that there is a functor which is somehow dual to K theory with respect to certain pairings, and which also has the cohomological property that it turns short exact sequences into long exact sequences. And so that I get a dual boundary map, which behaves dually in the pairing. Here I denote this pairing. And this is something which is, I think, more subtle. So let me just flash through, I think, the answers which I have seen in this context. The first answer, which is sort of the cleanest I find, would be just to say, okay, I take the KK dual, if you wish, of K theory, which is K homology. And since KK theory is such a fantastic theory, all the functorial properties go through and everything is fine. The only problem I would say with this is that it is so powerful that it's also very abstract. And when you do a calculation, you end up with something which, for instance, in the case where I have reals and produces Clifford values indices, these are mod 2 invariants. So yes, so again, this way seems to work perfectly, but it's difficult to really calculate, I would say. Other ways which are then, which I've seen is to look at the spectral flow of this boundary invariant, which is an operator which has spectrum in the gap. And if this spectrum in the gap comes from a family of operators, which are actually a curve of operators which have discrete spectrum, for instance, then you can calculate their spectral flow. And then you get numbers or mod 2 numbers. And the third one is using cyclical homology, which was the one which Nigel has already mentioned. And this third one, I think, was actually the first one which was implemented in the bulk boundary correspondence. And it's very nice also from the perspective of physics, because it gives us formulas. We saw some formulas in Nigel's talk. They were on submanifolds, but the formulas are very simple, very similar, and they can be nicely related to transport coefficients via Kubo formula. And the problem of this third approach with cyclical homology is that in the context of mod 2 invariants, they are useless because cyclical homology doesn't see torsion. So you need some sort of secondary pairing with cyclical homology. And this can be understood. I cut this a little bit short also, as saying that under certain conditions, my classes have always the property that they allow for representatives which have an extra symmetry, either an extra spin symmetry or an extra chiral symmetry. And then the appropriate invariant is what one calls a spin Chern number, which means I take a cyclical homology class or a Chern number and I dress it with a spin operator or with a chiral symmetry generator. Okay, so these were the ways how you could define numerical invariance. And now you ask the question, do these definitions actually satisfy what I wanted to have before, the coherence, meaning that I want to have some sort of dual to K theory? And then you find that again, everything works very well with KK theory, but already with cyclical homology, it's more difficult than it looked in the beginning, right? I mean, it works nice in the context of these extensions which I was talking about, I mean, which are Toeplitz extension or the Wiener-Hopf extension, but already beyond these extension, it seems rather intractable. And anyways, it cannot see torsion elements. And so there is a question. What do we do if we look at the famous torsion invariants? So let me just come up, therefore, with a couple of questions from which we can start the discussion, and which sort of I would like just to present here, and I hope for your participation in discussing these questions. So as I already told you, the first question which I would pose would be really basic question, namely, is the C-star topology really the right topology from the point of view of physics? I mean, we have learned from von Neumann that maybe it's the von Neumann topology, but if this is really true, then I can cross out all this approach because all these invariants would become trivial. And the second question, which is fundamental, which I think comes up now with studies on localization of one-year functions, namely that, is it really true that all the topological information is contained in such an extension? Shouldn't we look for more? It's a bit related to what Emil said. Shouldn't we have some other means than such an extension to get some topological information? Then you can ask a couple of questions which are specifically related to this program, yeah, which I try to lay out. For instance, I mean, how can we get, and can we formulate a dual to K theory which is computable and works also for the torsion invariants? Or more specifically, for instance, in the corner case, I'm not aware of the interpretation of a bulk invariance as a numerical invariant. So I don't see any dual side yet. Maybe somebody knows this. Maybe this has been developed and somebody can comment on this. So I think I leave the other questions like they are. They're quite general, and ask for your participation in the discussion.
Thank you very much, Johannes. I want to start with an observation because I see Giuseppe and Herman, they are still here. And one of their paper was a great inspiration for me, where they look for Dirac fluxes through a lattice and take the Hofstadter Hamiltonian and you pierce a flux quantized flux through the lattice, and you want to ask what's you want to describe the physics, and they very nicely formulated all that physics as the extension of the non-commutative torus by the algebra of compact operators. And these flux tubes are really defects. Although they are very different from geometric defects, they are really defects in a very generic sense. And as you can see, again, an extension, the whole thing is formulated in terms of a C-star algebra extension. Going a little bit further with connecting to Peter's talk, these defects that he showed us with the strings, they can, in principle, also be described as an extension, in my opinion, once we figure out what is the algebra of the bulk Hamiltonians that he was working with. So I was surprised when I learned that, okay, there is a cap on how many such topological defects there exist. It's almost like saying, okay, a lot of these extensions, in fact, are trivial. And perhaps they are trivial because they are, I'm not sure why, but to me, it should have been a family of infinite defects, which you can actually put on a different C-star algebra, and they are all described by an exact sequence. So the Bulk-boundary correspondence then really connects to this classification of extensions and so on and so on.
Who answers to this?
Nigel.
I'm going to answer with another question. I don't understand. You want
I don't
you
see
want
the
more
hands
extensions? You want a greater diversity of extensions, moduli of extensions, something like that?
No, so you see right here in this slide, we have this J. Well, you can extend by any other algebra. And in my opinion, that's a defect which you can define. So then, in fact, there is an infinite number of ways to extend an algebra, and you'll have to find what's the physical interpretation of an extension of A by some crazy algebra. But nevertheless, it fits perfectly in this model, in this problem.
If I understand correctly, these Dirac operators or phases you were talking about, they would define KK classes.
Yes, so once you fix J and A, then there are only a finite number of, I mean, this extension module that you wrote can be written.
But you said that J is attached to a point there, right?
To A?
To a point in the work of Hermann and
yeah, that's fine, that's fine. But that work sort of show that not just the geometric defects, but also these other types of defects can be also treated in terms of an extension problem. And in my mind, then I said, well, all this bulk defect is in fact a program in extension theory. And it doesn't matter if it appears at a particle level or a many-body particle level, it's this and only this. And
I didn't understand what you said there. It doesn't matter whether it's one particle or many particles?
For many-body particles, you started your talk saying that this is actually specific to one particle systems, non-interacting systems. But I see this paradigm actually applying in a very generic setting as just an extension theory of C-star algebras.
So you want to take the C-star algebra, which we learned from Peter, and extend it.
Yes, and classify then one by one. And I think by such extension, then if you go into a concrete representation of a Hilbert space, you will find, okay, what are these defects that you introduce via such an extension? And you can generate many, many types of defects. There is no limit on what kind of defects you can put on a bulk system described by the algebra A.
So you're saying A could be like a D-dimensional system and J could be a 2D dimensional system?
Yes, A should be a fixed algebra, is the bulk algebra. I'm thinking of it as the asymptotic system far away from the defect. So the asymptotic part is fixed, and then J now describes the defect, and it's the M is close to the defect, but A, so asymptotic region is fixed, that is A is fixed, but J is can be whatever you want. And then you can, on a bulk algebra, you can, on a bulk system, you can put an unlimited number of defects. You just
Emil, can I ask what is included in your terminology of defect? So if you couple with another system, other degrees of freedom, you call that a defect of the original system?
That's a good question, because
I had an additional spin or a couple of particles or a whole line of them.
Yeah, this is very, very, very special. You can caution out if you can caution out with an algebra morphism, the degrees of freedom that you put in, then it fits into such an exact sequence. So you can go from the bigger algebra E that you get by adding these degrees of freedom, and you can caution out those degrees of freedom by the map Q to land back into your bulk algebra, then will qualify as a bulk defect for me.
I see.
But many times when you put degrees of freedom, you actually, J is not an ideal, or it's just a subalgebra. So that's
so then let's go back. You said it doesn't matter whether it's in the one particle context or in the many body context. But so the defects that Peter said were limited in number.
Yes.
They say something very interesting. They say that the state space, the finite energy states of your system, that has all these degrees of freedom, can be built up from just a finite number of species, and then you can have different numbers. And there may be some rules about how to combine them. Mm-hmm. Very much analogous to the standard, picture of, band theory or whatever, fermions. I mean, you have your states and then you can start filling them. And that's sort of, having few is sort of the power of it. So I'm not sure that it would be very interesting if you have a description that says something about that's significantly more general. Maybe I misunderstand what you're trying to do. But why do you expect so many different kinds of defects? I'm not getting.
Yeah, for example, instead of using a lattice, we can use a lattice with a screw defect. Are you sure there is nothing new in that setting? And certainly this screw defect will be described by another extension.
Okay, it's a fair question. I don't immediately know the answer in general, what to expect, and there could be others. It doesn't sound natural to me that it would be
so,
infinite classes of them.
Other questions?
yeah.
Could I offer one example? Yeah, so hi everyone. Which looks tantalizingly like it would fall into this program, but seems to be quite tricky in terms of the details. And this is simply the example of the domain wall Dirac Hamiltonians. So for a long time, I guess since the 60s, people, this goes under the name of the Jekyll-Rabbi Hamiltonian in one dimension. And it's very closely linked to the so-called SSH model in the study of these polymers. Now, the point is that this comes from a Dirac Hamiltonian in one dimension, and the defect there is very explicit. There's a defect at the origin, and what it says is that the mass term is different on the left side of the defect in sign from the mass on the right side. And whenever you have this switching of the mass, you can prove via an index theorem. So this is an ordinary index theorem in terms of the Fredholm index, that there will be a zero eigenvalue. So there will be a localized zero energy state in this so-called massive Dirac Hamiltonian. So normally you expect a massive Dirac Hamiltonian to have a mass gap, but when you have a domain wall where the mass switches on both sides of the defect, then you can actually get this index theoretic zero mode. So the main difference and difficulty in applying this C-star algebra program is that you're dealing with unbounded operators. In fact, unbounded in both directions. So it's not bounded below. So the constructions of these Fermi projections and so on don't quite make sense. But nevertheless, you can still do a little bit of stuff. This C-star algebra formalism to recast these Fredholm indices in terms of C-star algebra extensions. In this case, it's kind of the trivial one, which everyone knows, which is the extension of the Kelkin algebra by the complex, for which the connecting map is simply the ordinary Fredholm index. So this is a very concrete example in which you can solve the spectral problem exactly. And if you want, there's an index formula via the Kalyas index theorem. And in fact, I think these examples go up in higher dimensions as well. So there exists, I guess, kind of a whole class of examples that fall under this, what one would call defects. And so this is to present one possible class of examples where there's a bulk defect correspondence, which hasn't, I think, been written directly in terms of what Johannes has presented.
Yeah. Series of work of Guillaume Ball on that.
Yes, exactly. Yes. So so they didn't quite use the index theory method. So they were trying to get more refined information about the spectrum, in particular how fast the zero eigenvectors decay, so quantitative estimates. But generally speaking, there's a quick way to show that there are zero modes which are perturbation invariant.
Okay. So you're telling that this example fits or does not fit in this
example? It would appear to fit in the sense that there is some index theory in the background. And you can sort of put it into some sort of exact sequence, but it's not very well tailored. It's not as precise as what Johannes has presented. And in some sense, it's not directly necessary, but it gives another class of examples. And the main point of departure is that these involve the unbounded operators, unbounded both above and below. So there may be some small difference in terms of connectivity properties of the spectra. So for example, Nigel in his talk was precisely talking about these things. And there is a difference in whether these unbounded self-adjoint operators are disconnected in spectrum. For example, at infinity. So usually they're connected in infinity when you are in this unbounded setting, and that seems to make a bit of a difference. So sorry to kind of
go on.
Discuss of examples.
I recall that Serge Richard, he did a Levinson theorem with the Friedrichs operator. And, I think this is also a perturbation of an operator which is covering the whole line in spectrum.
Mm-hmm. Oh, yeah. But this domain board Dirac Hamiltonian has spectral gaps. But it has
but you're speaking about the difficulty of having spectrum up to plus infinity and minus infinity, right? Or did I misunderstand that?
No, I'm talking about the difficulty of studying from a homotopy theoretic point of view, or from the point of view of connectedness properties of spectra using NCG tools. The Dirac, the first order type of the Dirac operators, for which typically you don't have the unbounded from below, bounded from below condition. So you don't have a positivity condition. You don't have a semi-boundedness condition on your operators. Of course, this would be for continuum models, not so much for lattice models. Yeah.
Herman, can I ask you about your new index? So your work with Terry. You mentioned that it can be extended to many-body interacting framework. Can you explain quickly how it will go?
Oh, you misunderstood me. I did not say that I know how to extend it to many-body framework, but I said I would like to discuss how one could do that. Because basically what this does is in the non-interacting setting to put the topological Hamiltonian in a trap, which is sort of not a harmonic trap, but it's a linear trap. So like a Dirac operator given by the position operator, and it localizes all the topology in finite volume. So I was wondering whether one could do anything like that also for many-body systems. What would happen, and if there is any topology surviving if you put your many-body system into some sort of like a Dirac trap, as I said. For that, maybe I should explain more in detail how it works.
Can I also say, is it important that the Hamiltonian on the lattice has bounded spectrum for this trap, or just to connect with the previous?
I don't think that's required.
No, I don't think so either.
Okay. So that's a good we pass one.
However, you do need, for the rigorous proofs, what we do need is a gap, or at least some sort of a localization estimate. Yeah.
So one of my puzzles is that if you take the non-interacting insulator, you put the chemical potential inside the gap, you calculate the many-body spectrum is unbounded from below and above, and the gap, in fact, happens to drifts all the way to minus infinity. So even in these very trivial systems, this gap condition and localization is very difficult to formulate. Because at the end, as you take the system larger and larger, you start to occupy negative and negative energy more and more. Therefore, the ground state just go down to minus infinity, and the gap happens at minus infinity. So this condition of existence of a gap is really drastic.
So this problem that Emil was saying already occurs in the infinite Majorana chain, for example, one of Kitai's many models. So the so-called particle hole pseudo symmetry means that you don't really have this finite energy ground state in the infinite chain limit. It goes all the way to minus infinity, as Emil was saying.
Yes, but in that case, you have a gap at 0 energy. In this case,
Sure. But for the ground,
also the gap drifts to minus infinity. So there is no.
Even worse. Okay. Right. Okay.
So that's so unless you have a the occupied space has a flat, the spectrum is fully collapsed to a point. The spectrum below the gap is fully collapsed to a point, then you cannot impose this gap condition.
Okay. Is Ralf Meyer still there?
Let me see. Okay, so Ralf now.
No. I was wondering whether anybody could comment on this question, which I put down for the Bulk-Kohner correspondence, namely whether there is a dual side, whether there is a cyclical homology formulation of this problem.
So I see Shin is here.
Yeah.
Hi, Shin.
Hi.
So have you thought about?
Well, I think I can't hear you.
So can you hear me?
Oh, yes.
Okay, so the question is, if you look at the list of questions which I put up there, is the fourth question. So in your model for the Bulk-Kohner correspondence, have you a dual theory in the sense that you can apply cyclic cocycles to these elements and a dual boundary map?
No, I haven't tried. I mean, I have extension, but I haven't do that direction.
Does anybody have?
I don't know.
I forget the name, but the algebra that appears for the bulk edge invariant, this pullback Caesar algebra, you can look at the cyclic homology of that guy. I forget who did it, but it was done in the early 90s, I think. Park, I think. But I haven't.
Oh, yeah.
Okay.
But maybe that's just for the bulk, I think, or bulk corner. Sorry, bulk edge invariant.
I think it was Park and Walters, no?
Efton Park.
Yeah, and Walters together or not? I don't remember. There was some other author.
Maybe could. We'll research and see.
Maybe Nigel can answer this question. I mean,
if I knew the algebra.
Yeah. Well, so what are the chances that you can set up a dual sequence in cyclical homology?
Well, in a certain sense, 100%. There is excision in periodic cyclic homology, so you can always just do it. Calculable. People have tackled some remarkably complicated calculations in cyclic theory, so it's hard for me to believe that this is would be beyond reach to calculate in geometrical situations related to a sector in R3. But of course I didn't do it. I'm just expressing optimism.
Okay.
If you have some cyclic cocycle attached to the ideal, and now you want to transgress it, so it's now a cyclic cocycle for the quotient algebra in some extension. You want to calculate what it is you get. In situations like this, it's hard for me to believe it couldn't be done. If you pay me enough money, I'll recruit a graduate student to do it for you.
Okay. I mean, I think it should be interesting to know what it is. I mean, I understand. I mean, the cycle on J is the standard cycle because it's essentially it's a circle. On the corner, you have essentially the circle, so you have just the winding number cycle.
Yeah. Fair enough. And
now you have to pull it up to the way to this pullback algebra, which replaces the bulk algebra.
Can you describe what it is?
Well, you have this
mathematically.
The corner is cornered by two planes. Okay, so I have 2 times a system with a triplets extension. Okay. So I have one generator which makes one triplets extension of the Z, and the other makes the other one. And so these 2 extensions, they both factor onto the same algebra. And so I take the pullback algebra, this universal algebra which you can fit in the corner of this diagram. Is this understandable?
I'm beginning to, I think I understand. But you're just talking about the triplets extension, and you're manufacturing one extension out of 2 copies of the triplets extension. Is that a fair summary?
Yeah.
Yeah, in a way, yeah. So these 2 triplets extensions do not play part in the extension which you write down, which is the GEA extension.
Okay.
They are just made to fabricate the algebra A.
Yes.
So the algebra A is the pullback of these 2 triplets extensions.
So let me understand. Can I just interrupt you then? Your algebra A consists of pairs of elements, one in each of 2 copies of the triplets algebra, which have the same symbol, same map to the same thing in C of S1.
Yes.
Okay, and so that maps to C of S1, and now you just take the kernel, and that's your J.
No. I have 2 generators.
Yes.
Each one has its own triplets extension, but the quotient algebra is the same.
Yes.
And now I'm looking at the algebra, which when I make a square out of these 2 triplets extensions with the corner, which is the pullback algebra of that.
Which you call A.
And this is A. Okay, this I call A. And then this one is the ideal of is the quotient of an extension, which is the quarter plane triplets algebra.
Of this A here, I see. Okay. Yeah, okay, I think I understand. Yes.
I mean, in principle, it's always the same building blocks, but they are cleverly put together. And maybe Shin can explain this better because it is due to him.
And now you simply want to transgress this one co-cycle on this ideal, which you say is essentially C of S1. I guess C of S1 tilde K, something like that. Okay. It's an assignment.
Okay.
So let me make a comment also. I think Johannes is completely right that for all sorts of defects, one ought to be able to come up with an exact sequence. But as we learned right now is that each time that you try to attack one problem, you should write a paper about it and construct this explicitly the exact sequence and then the associated cyclical homology, boundary maps and so on. So it's not easy, and each example in itself is interesting as we know. So for example, I mean, in the chat you saw there was a comment on a paper by Kubota recently where he looked at screw defects. I'm not sure whether, I mean, I didn't look in great detail in the paper, but that's another example where you can build up the exact sequence and okay, then I think the part on the cyclical homology side and the evaluation of the K-theory invariance is a bit short in that paper, and to be honest, I didn't really understand how he did these things. but once again, I mean, this is a worked out example, and each worked out example is interesting, but it's a job, you know. It takes weeks, and if you're not experienced, take months.
Yeah, I don't doubt that at all.
No. I mean, this was just.
But it's very interesting, because once you have things explicit, as I said, through representations of Hilbert space, I can, for example, advise the people in the lab how to build these systems. So each examples where we know is fundamentally different from the other is extremely important.
Just a comment about this particular problem on a quarter plane or a quarter of R3 or whatever. I skipped one page in my lecture in which I discussed residue traces and the Radul cocycle. The place this Radul cocycle comes from is exactly related to this. The algebra of pseudo-differential operators is an extension by some algebra of smoothing operators of the algebra of complete symbols. And if you take the trace on the algebra of smoothing operators, which is a zero cocycle, and you apply this co-boundary process to get a cyclic one cocycle on the algebra of symbols, so you solve the problem that you were just posing to me before, then what you get is this Radul cocycle. In other words, there are calculations similar to the one that you're asking for, which have already been done, and they involve I don't know, most naturally or most immediately, a piece of machinery which I didn't talk about, but which I did write about in the slides for my talk. So there are multiple possibilities to carry out this calculation, which is not the same as actually doing it, but looks quite doable to me.
Okay, thank you. Another line of comments, thoughts, questions?
One of my hope will be that this bulk boundary correspondence eventually can be formulated directly on the automorphisms groups generated by the Hamiltonians. Somehow, I have no idea. But in that case, that will solve, I mean, the transition from non-interacting to interacting will be trivial, and it will make, the setting will make no difference whatsoever.
What are the examples in those settings? And do we know what the result, at least qualitatively, what it should be in terms of the boundary? So presumably there's some sort of half-infinite system, for example. So for the spin chain models, for instance, is there some result we know for the half-infinite version of that?
If anything is known?
Yeah. For example, not using a big machine, but at least on a case-by-case basis, a specific model, for example. Maybe a chain of spin halves, for example.
Yeah.
So half infinite.
We have investigated numerically for example, on CAR algebra, which and dynamics, which conserves the number of particles. That is the gauge symmetric part of the CAR. And then we went on with n particle sector one at a time. And then bulk boundary correspondence then can be formulated in each of these sectors. And of course, as you go up in the number of particles, it gets more and more complicated.
There's something non-trivial known in other than in the single particle sector, for example.
Yeah. So the K theory which are involves grow. The number of generators starts to grow with the number of particles, and the bulk boundary becomes very rich.
So can you explain that?
can I make just a quick comment? So one of Yoshiko's papers from a few years ago is just about one-dimensional spin chains and matrix product states, well, which are approximated by matrix product states. In one of those papers, she showed that the edge mode degeneracy is invariant under this, quasi-local, quasi-adiabatic continuation if you just have a half line of spin chains. So that's kind of a bulk boundary type result for the spin chain picture. But I mean, you are kind of right that there isn't a lot of, certainly compared to the single particle case, it's there's not as much known, I think.
So Chris, in those examples, it's again this particle number conserving Hamiltonians. What I'm thinking of is a Majorana chain, for example, and this old work where there's some change in the mod 2 index of the infinite Majorana chain when you add in these interactions. So whether one can make a bit more precise sense of this change. I think people claim that you have a Z mod 8 index and it's somehow related to some very interesting geometric invariance as well. So that's sort of the background behind why I'm asking about the specific models, whether they include this Majorana chain examples.
Yeah.
Yeah, as far as I'm aware, these Z mod 8s and Majorana type guys, I mean, I know how one is able to see these invariants only in the sort of bulk type or system without edges, at least mathematically anyway, which is probably not to say that it can't be done. It's just, as far as I'm aware.
In Peter's talk earlier in the morning, I guess, is does it not include examples of the local algebras are these CAR, the kind of standard CAR algebras or Clifford algebras?
I mean, you just run into, oh, sorry, maybe Peter can answer, but there are slight differences if you choose the spin algebra versus the CAR algebra.
There's some formalism as well, right, to do with this. That's exactly what I was talking about. So I don't know if it's included in sorry, you can answer the question.
Yeah, I didn't talk about this myself, but I mean, the framework and principle that you can do this for CR algebras as well, I think, but I'm not sure what you would get then. But yeah, I mean, most of the techniques are there, I think. Yeah.
Okay. But the precise theorems are not are they available somewhere, or it's not been studied in detail?
No, I'm not aware of it now.
Okay, thank you.
But let me ask a question, Chris. The Z8 invariant in the Majorana chain with time reversal, is it? I think. Do you have?
Yeah. So you need an antilinear action. Yeah.
Antilinear. Yeah. Okay. So do you have a spectral flow interpretation there of the Z8 invariant as well, or not? I mean, like we did in the 1D case with just parity, there was a Z2 flow that one could localize. Is there something similar there for the other symmetry classes as well?
You might be able to construct a sort of domain wall type picture, but maybe in the 1D case, this is a bit trivial. I mean, the short answer is I don't know right now, but it might be possible.
Yeah.
But I think the statement about Z8 was that the the classification on which the invariant took integer values, then it just reduces to Z8. So these are not different classes, but it's rather the range of the invariant. One has to look careful about that work because they seem to.
That's not right. I think you can. I mean, the way that I understood it is the way that the number of stacks that you take of the 1D systems,
yeah,
modulo 8 is a different. I mean, gives you 8 different phases.
That's right. And
if you don't know from the very beginning in which phase you are, you would like to be able to detect in which one you are by, say, doing some local transformation which leads to a spectral flow.
Mm-hmm. Yes. Okay. So we are talking about the same thing. Yeah. I'll be cautious about that work because it looks like they enable any possible interaction. So as we all know, if you allow the transformations to be in the whole B of H, then everything can be connected to everything. So of course the topological invariance will reduce to 0, or because if you look what type of interactions they allow, they are quite wild.
I mean, you can prove this quite rigorously because you're in the 1D case, you have the split property. So you have a graded type 1 factor and you have a real structure on this graded type 1 factor. And then you're just asking, okay, how many different types of, up to some sort of unitary equivalence, you know, how many different graded real type 1 factors do I have? And you have 8. But I mean, it's true, that's quite a coarse classification. Maybe you want something that's a bit, that retains a bit more, for lack of a better term, local information.
So you get a Z2 index, isn't it, Chris, from what you said?
Because you have the real structure, you get to Z mod 8.
Oh, okay, Z mod 8.
So on the topic of more examples, I recently learned about this helium-3 superfluid in 2 dimensions, and I don't know if whether email knows anything about whether it's known that whether the H states in those examples are stable. At least mathematically, you might expect something to happen there. You go to all these classification tables, you have a Z invariant for the 2D class D superconductors or superfluids, and then in some early papers, the physicists predicted that you could get these H states there. I don't really know the literature on this, so I just wonder if there's a chance that these things are topological H states. Anyone knows?
Yeah.
Hey.
So, new questions, new comments, new questions, new comments.
Yeah, there was a question from Go Chuan. Anybody?
Anything knows about these 2D superconductors or helium-3 things?
Can yeah, I don't hear you very well. Can you speak a bit louder and
Oh, sorry. Yeah, it's a bit late here, so I didn't want to cause too much noise. So in class D, in 2 dimensions, there is a Z invariant, bulk invariant, and I believe this is realized by one of these superconducting systems, or even in superfluids. I was told it's got something to do with helium-3, and then it is supposedly also known that there, or at least theoretically, that there are H states there as well. So this might be an example of bulk H correspondence, which can be handled, which doesn't involve any kind of horrible torsion invariance. So I just, my question was whether anything is known about how stable these things are, and there's actually interest.
Just to understand properly, you are referring now to one particle models. I mean, or
this is in one particle models. Yeah, although a lot of things in that direction are in principle formulated in a way which can incorporate at least some weak sort of interactions as well.
And when you say Z8, you mean
oh no, this is the Z,
that
Z
to the power of 8 or that mod 8 or?
No, this is just Z. It's not. I'm moving on from Z mod 8. Yeah.
Can I comment on this, Johannes?
Yeah.
So this is actually just like the theory of the quantum Hall effect. Indeed, you do implement symmetries, but these symmetries don't break the theory of the quantum Hall effect. So actually on several of these superconducting phases, BDG type models in dimension 2, you find something in a paper by myself and Giuseppe from 2 years ago or so. It's called, I mean, there's this boundary correspondence worked out for these class D systems.
Okay. So this is from when? 2 years ago?
Yeah.
Okay, I'll take a look.
There's no torsion.
No, there's no torsion. I mean, these are Z invariants, as he said.
And is it with cyclical homology in the dual side?
Yeah, but it's for you, it's boring. There's nothing interesting happening. The real symmetry is irrelevant, so to say. For it's the complex theory which is relevant, which carries through.
Are you saying that there's a relation with the quantum Hall effect?
Yeah. This is exactly the same physics and also the same math, actually.
So if I break the charge conservation in the quantum Hall effect, I get this class D thing.
Hermann?
Yeah, I'm thinking what the right answer is. I mean, the standard model for this is what the people call the P plus IP superconductor phase.
Mm-hmm. Mm-hmm. Yeah.
Yeah, but to set it to get a one particle operator, then you do need a particle Hall symmetry.
That's right. Yes.
Okay.
Since we are asking about models, is there any model, I mean, I'm not so firm in that, in 2 dimensions with chiral symmetry, the complex, which has an interesting invariant?
Yes, I mean, semi-metals. The weak invariants in semi-metals, like graphene.
And they live in K1 or?
Well, it's not K theory. It's von Neumann theory. So
Von Neumann theory.
Well, I mean, okay, you can't formulate it purely in C-star algebraic framework. Okay, you look at invariants for projections which do not lie in the C-star algebra, but are sufficiently regular that you can still pair them with cyclic co-cycles. And then you get for these systems weak invariants. And actually, I will mention this in my talk next on Wednesday.
Johannes, I can formulate an interesting Bulk-defect relevant to this class that you mentioned. You have the lattice, it's 2-dimensional. You take a quarter of the lattice out and you join the boundary, making a cone with a tip singularity. It's a singularity, it's a defect. If you calculate the transversal of this thing, you'll find that the transversal has a disconnected part, and at the asymptotic part, it's a circle. And therefore, in the asymptotic regime, you get the 2D model plus this circle around. So you move from 2 dimension to 3 dimension, and you have the chiral symmetry present. And then if this 2 plus 1 system has a non-trivial bulk invariant, then there will be a mode, a zero mode on the tip.
So have you written this up already, Emil, or not?
Yes, I have, and I show that this defect is equivalent to the 3-dimensional Dirac KK cycle.
So there's a draft somewhere, yeah, or a paper.
You mean the K-homology class? Huh?
Yeah. And as you know, this kind of defects, you can put 2 of them, 3 of them on the same plane. So they really go by, they are really classified by this KK group. And the trick, I mean, the idea is very simple. You look at the transversal not of the bulk system, but rather on the system with the defect. And this system is can be decomposed in has minimal components, and the minimal components gives you the asymptotic algebra. And then
minimal components under which action?
Ah, okay. Then I should take away because there is no action. The whole always comes. I mean, in these examples that I studied, the transversal always decomposes naturally in an open set and a closed set. And for a groupoid, that immediately gives you an exact sequence, and you can formulate the bulk defect. The bulk defect formalism, no problem. Particular for this type of what is called rotational defects, this solves it completely. So then this, looking at the groupoid for the groupoid specifically for the transversal with the defect gives you the solution of the problem. The transversal has several manifolds, smooth manifolds, then they are connected through disconnected parts, and therefore it's an extension problem by compacts again.
So we need a blackboard. I mean, you see the limitations of virtual discussions. Or we should all be better equipped, and everybody has, I mean, his tablet. I mean,
so, yeah,
otherwise, I mean, you speak in the air.
We can share things. If I don't want to abuse, but if you just show, I show you a picture, you will see immediately what I'll be talking about. So this is the picture of the transversal for the general case. We can go to the just one-dimensional case with an edge, and in that case, the transversal is just a bunch of points, and then you have the limit point L infinity. And here is where the bulk algebra lives, and all this is part of the defect. And then in the groupoid associated with the half system, then the transversal divides easily into a point and an open set. Therefore, in the algebra, as always with the groupoid algebra, that sets in motion an exact sequence, and that's the end of the story. You know very well from here on. In particular, if you take a defect like this, then the transversal looks like so. So you have now here it's if you look what is the algebra corresponding to this circle is just mappings from the circle into lattice models on 2D, and if you construct a non-trivial model on this line, you can start to see the zero mode appearing exactly on the tip of the defect. Like that. But no, where we started all this from somewhere, but what was it?
Well, my question was to have a two-dimensional model with chiral symmetry and an interesting invariant which lives in K1.
So here the model, I can show you what the model is. It's really it's taken from the.
Oh, that's one of these models, okay.
Yeah, three-dimensional model in A3 class, but now one variable, in fact, is the coordinate on that circle. And if you put down this Hamiltonian, then you see that in the asymptotic limit going down along the cone converges to the strong generator of the A3 class, and then you have this. So now if you write the bulk boundary correspondence, then this extension class is in fact the three-dimensional Dirac operator, the same cycle. And we know that because it pairs non-trivially with any K-theoretic element which involves the any dimension. So it has to be the top cycle.
So it's, and therefore it's in K1, or because it's three-dimensional.
Yeah, that's right. So it's
okay.
So it lives in this, but here, what can you have in here? They are only 4 generators. It's the Dirac operator with 3 coordinates, involving 3 coordinates or 1 coordinate, certainly is the one that involves the whole 3 coordinates. So that's the defect.
Okay, thank you. I'm going to read this. Is there?
Thank you.
Is it possible to share screen with people?
Yeah, yeah. Can.
Yeah, of course, it's disabled screen sharing.
But,
let's see. Yeah, I don't think I can share the screen though.
So did you press the button share screen?
Yeah. Now I think it's okay. Right. So I can do some constructions with continuum models of this higher order topological insulators, and actually you can write down some explicit examples in which you can calculate that you have a Fredholm operator and you have a localized zero energy. eigenvector. And here's a class A tree example in 2 dimensions. So the operator is quite explicit. As I pointed out previously, in these examples, you don't have this Fermi projection construction, and it's not very clear in what algebra you should have some operator associated to such unbounded operators live in. But you expect to be able to construct a K1 class out of this. Yeah, but I'm not sure in what algebra. You may have to use some row algebras, for example. But the construction is basically using the analogy that the SSH model is the lattice version of the Jacques-Rebbe domain Dirac Hamiltonian. And if you mimic that construction, you can easily construct this Hamiltonian that I wrote down and solve for the spectrum explicitly. And it has this corner localized in the corner. The solution is quite explicit as well. So there are some examples, but this is Dirac type operators, and I'm not sure what C-star algebra you should associate to this operators.
Just a question, how does M depend on X and Y here?
M? Oh, if you restrict it to the quarter plane, then it's just M. Otherwise, it's M times the sine of X times the sine of Y, if you regard it as a sort of domain wall operator. So there are four quadrants, and the sign of the mass term depends on the signs of the X and Y coordinates. Yeah. But you can restrict all these operators to the upper right quadrant, in which case you simply have this single mass term. There are certain boundary conditions you have to impose as well, which become relevant because you're dealing with these differential operators. But
you can say you cannot put this one on the lattice.
No, this is the continuum version of how you construct the higher order topological insulator on a 2D lattice. So you take 2 copies of you take some sort of external product of the SSH model essentially. So in the X direction, you have the SSH model, then you add the SSH model in the Y direction, handled with the grading operator.
Then the question is, why did you go to the continuum model? Just for the sake of it, or?
I have some other reasons, because I want I found that the boundary conditions are quite important in these examples. And in 1D, I had wanted to also understand to what extent the Jacques-Rebbe Hamiltonian is really the continuum limit of the lattice.
Just a comment, you did take a look at the paper by Jean-Michel Graf and Clément Tauber and Jude?
Yes, yeah.
Because there also these type of models appear with boundary conditions do play a role.
Yes. So in the continuum, in fact, they advertised that paper as instances where the bulk H correspondence, at least when formulated naively, were not quite whole. Depends on how you count, how you assign topological invariance, both to the bulk and to the boundary. There's a strong dependence on the boundary conditions there. But quite essential to the situation there is that you have this unbounded spectrum both above and below. And I think that causes some sort of anomaly. Probably Johannes has some point of view in terms of scattering theory, or this sort of anomalous bulk H correspondence, if you want. Although the word anomaly,
yeah, I think it's a misnomer.
I'm sorry?
Because the S matrix has a contribution at plus infinity.
Yes. Yeah.
And so if you do I think if you take this into account, then it's a perfect boundary correspondence. So
right. So it's anomalous, but you can write a theorem which produces which counts contributions.
If you decide that to excart what's at plus infinity, then it's anomalous. But you should take it into account, and then it's normal.
Okay.
If you remember that, also if you have these one-point interactions, right? So you look at scattering theory with delta potentials.
Yes.
They also have contributions to the Levinson's theorem, which come from energy plus infinity.
Right, right. Yeah,
So
are you talking about
if you,
or
sorry?
Are you talking about, for example, a Laplacian with a delta potential or something?
Yes, exactly. Laplacian plus delta.
So by the way, the square root of that is the Jacques-Rabbi Hamiltonian. So there's a connection to the.
Okay.
Yeah, yeah. If you square the Jacques-Rabbi Hamiltonian, you get the Laplacian on the line with you get two copies of the Laplacian on the line with a delta potential, but they are shifted with, by some overall energy. So it's sort of the Dirac operator for the Laplacian with a delta potential. Yeah, it's kind of first order square root if you want.
Good connection.
Yeah, that is one of the ways to the index theory way to see the zero mode actually. Is this supersymmetry argument about the spectrum. So the spectrum is the same, symmetric about zero, except possibly for one extra zero mode in one of the two sectors. And this sort of structure seems to be quite generic.
I think it's slowly coming to an end. People are sleeping.
Right. We are down to 13 brave people here.
Yeah.
Well, we'll see if we can keep up for 4 more days.
Yeah.
So, Nigel, what do you think it's the mathematics community getting things out from the talks?
I think I'm absorbing something, yeah, but it's going to take a while. Hopefully, by the end of the week, I'll be less confused than I am today. But thank you. No, it's been a very useful experience listening to you guys.
It's so it will be always like that. Things come from physicists. They are not well formulated, and they are not well formulated because when something becomes well formulated, that becomes old and it's left behind, and these things. So yeah, we have to somehow navigate so many things.
Yeah, but yeah, when it becomes well formulated, that's when we just get interested, but then you're off somewhere else. So
yeah,
it's hard to keep up with you guys. But very interesting. Thank you.
Well,
okay.
thank you.
As the moderator, or how you call that?
Bruno.
I say goodbye to everyone. And so, yeah, hi, I see Bruno. He turned on his camera. Well,
just to be able to say, yeah, it was a good start, and we had wide-ranging discussions, and it was clear that there will be even more topics mixed into this in the coming days. So
yeah,
looking good.
That's nice. Okay. Yeah, tomorrow, just to remind, so it's the talk by Chris. It's for non-interacting fermions, but it's very interesting how he will hopefully teach us how the Hamiltonian entered only as a grading for this thing. So, and then from Lucas, the classification of correlated phases, and then the discussion moderated by Anton. So I think we'll get to it.
Yeah.
Okay, thank you.
I wonder how the Japanese people do this. I mean, it's in the middle of the night for them, right?
Yes,